Now we're going to move on to the third part of Chapter 24, where we're going to talk about interference of thin films and interference due to reflection and refraction. So first we're going to start out with the reflection and what interference looks like when we have light reflected off of a surface. And the first experiment was done by a fellow named Lloyd, so it's called Lloyd's mirror. And basically what happens is that as we get a reflection, the light that travels, the reflected ray travels a different distance and is also reflected. And there's some interesting behavior that goes on with this reflection in that reflection will often, not always, but often invert the ray. So it will act like it travels half a wavelength farther than it actually does. So an interference pattern is formed by bouncing light off of a surface, just like what we've seen with the single slit and double slit and diffraction gratings. And there are patterns of light and dark fringes, and it's slightly different because there is a 180-degree phase change due to the reflection. So we're going to get into why that occurs. So it occurs basically the same if we think about a macroscopic wave. We talked about this last semester, that if it is a hard intersection, the wave will be reflected in the opposite direction, will be inverted upon reflection. And for light, this occurs when N2 is bigger than N1. So thinking air going into water or glass or anything else. If, however, the wave bounces off of something that is squishy or bendy, so for a string it would be this ring on the pole where it can move up and down with the wave is not inverted. So the equivalent case for light is that N2 is less than N1. So if we're in glass, in water, in plastic, and going into air, that reflected ray is not inverted. Okay, so let's look at an example where we're looking at what's going on with the reflection of this helicopter. Here we have a 60 kilohertz electromagnetic wave. So it's not light waves, but it is something that is an electromagnetic wave. And we know that there is a phase shift when the wave is reflected. The direct path is 21 kilometers, and the total path length bouncing off the helicopter is 19 plus 12, so a total of 31 kilometers. So we want to see if the helicopter caused constructive or destructive interference. To tell that, we need to see if the wave lands in phase or out of phase. But the first thing we need to do is figure out what the wavelength is. So we're going to use our wave equation that we've seen lots of times before. Lambda is equal to c over f. And again, c is 3 times 10 to the 8th meters per second, and our frequency is 60 times 10 to the 3rd hertz, or cycles per second, and that gives me 5 kilometers. Now the path length difference, the delta is 10 kilometers, which was 31 minus 21 kilometers, gives us a path difference of 10 kilometers, which is in fact a multiple of 5 kilometers. So if there is no phase inversion at the helicopter, then in this particular case it would have been constructive interference, but here we do have that phase inversion, so it's acting like it's traveling half a wavelength farther. So in this case it's going to be 5 over 2, or 2.5 kilometers farther, and so therefore we're going to have destructive interference. And here those values are again nicely typed up, and we do have destructive interference because of that phase inversion upon reflection.